Electrochemistry. It says review terms. Have we talked about these before?
Some of them,
Okay.
oxidation, reduction, stuff like that, agents.
So it must have been in a previous chapter. We hit it a little bit. Okay. Oxidation is loss. Reduction is gain. And electrochemistry studies the interchange of chemical energy between chemical energy and electrical energy. And anytime you have a redox reaction, electrons are transferred. Not all reactions are redox, though. There it is. Oil rig. Okay, our rules, in order to determine how the electrons are moving, we need some rules. And we assign oxidation states to each element in a reaction. Not necessarily because they're ions, but it's more of a bookkeeping scheme just to track the electrons. So we can assign oxidation states to covalently bound elements. First rule is the oxidation state of any element in its standard state is 0. So if you have metals like aluminum, its oxidation state 0. If you have diatomics like that, oxidation state on each one of those hydrogens is 0. If you do have an ion in a reaction, then its oxidation state is the charge on the ion. If you have oxygen in a compound, any compound, as a matter of fact, we take its oxidation state as -2. So it may be combined with something else. It's -2 unless it's combined with itself and then bound to something else. In that case, it's a peroxide, and each one of these is -1. So that means the whole thing is -2. Okay.
So an oxidation state would be like how much is lost, right? How less it is.
It's a relative term for its number of electrons. This would say that it's excess of 2 electrons. But it's not really a charge, not necessarily a charge. For these, it is a charge. But for everybody else, it's just a bookkeeping scheme to keep track of the electrons. Hydrogen. Hydrogen in a covalent compound like water is always +1. And that makes sense. Oxygen's -2 to balance them. If hydrogen is bound to a metal, like let's say, trying to think of an example. Nickel hydride, then it's -1. That's not up here. But that's an ionic compound. Covalent compounds, hydrogen is always +1. Fluorine. Fluorine is always -1. When it's in a compound, it's -1. The other halogens, sometimes we have to assume if, say, chlorine is bound to something else, like phosphorus, then the place to start is, say, just call chlorine -1 and go from there. So sometimes with these rules, we're sort of stuck, and unless we make an assumption, we can't move. For neutral compounds, the oxidation states have to all add up to 0. And for polyatomic ions, they have to add up to the charge on the ion. We'll do some examples. right now, as a matter of fact. Okay, so let's see. I think I left one out. I did. All alkali metals, first group, they're always +1. And then the oxygen's -2. So we have -14 for the oxygens, right? 7 times -2, and 2, that's +2. So we have -12 that has to be balanced by positive for chromium, which means +12 total or +6 for that chromium. Here we go. How about CO3 2? I think I'll do it over here. This erases better. The carbonate ion. In this case, we have to add up to a 2-. So 3 times 2- is -6. But we have to hold 2 of them out for that. So we really only have to balance a -4 with that carbon, which makes the carbon a +4. Then you can check it out. -6 and +4 is -2. How about MnO2? So this would be a -4 total. That means this 1 has to be a +4. So the name on that would be manganese 4 oxide.
This is where you gotta put the little minerals in parentheses or something.
Yeah, type 2 compound. PCl5, okay. Here's the one where you have to make an assumption, because we don't have a rule for that one. So you just have to assume that this is -1, which makes this one +5. SF4, that's an easier one. Fluorine is -1, so sulfur has to be a +4. Now you'll notice in the periodic table, in each one of those boxes, there's a stack of different numbers. Some of them are minus, some of them are plus. Those are oxidation states, unless it's an ion. If it's an ion, then it could be any one of those. But it's more likely that if it's in an ionic compound, the top number is the one that's applied. It's all over the place. Yeah, it can be. So the top number in nitrogen is -3. So if you have a nitride compound, say with a metal, let's see. I would get stuck trying to figure out which one would be a good one. How about iron? Like that. This would be a 3+ and this would be a 3-. Like iron 3 nitride. In that case, when it's bound to a metal, the nitrogen would be -3. Okay. So now that we know the oxidation states, and we can determine whether the reaction is an oxidation or reduction or not, then we can use that information to make balancing the equation easier. If you just try to do the standard budget method that I've given you in the past to balance an equation, sometimes it's almost impossible to get a redox equation to balance. Because usually, if you've got an unbalanced version, it may be missing some things. And usually it'll be missing hydrogen ions and water. So it'll say that plus that yields this plus this, but you know right off that there's oxygen over here, there's none over there. So we've got this half reaction method that fills in the gaps. And what you're doing is you're splitting the overall equation into two separate, a reduction equation and an oxidation equation. And then you go through a procedure to balance. Yeah.
Oxidation has a plus 5e.
Yeah, plus 5 electrons. And the reduction, see, the 5 electrons are on the product side. So this had to lose electrons. Now they're over here.
Because it's oxidation.
And the reduction is the other way around. Yeah. And they have to be equal.
I had said they lose 5 irons.
Not necessarily. Could be. Well, there are 5 irons, plus there's only 1 electron lost for each iron. So 5 times 1 is 5. This is just to illustrate how you split them apart. We're going to actually balance one with the method. These are the steps that you go through, but it makes more sense if I just do an example. And there's a flow chart. So let's do this one. I'm going to try to fit it in this small space. Okay, I'm going to take that one. Well, we need to do the oxidation states on each of the elements to find out which ones, which reaction is oxidation and which one's reduction. So I start off with the easy ones. That one is easy. This one is -8. We have to hold 2 out, -6. So this is +6. And oxygen is -2, of course. This one is -6, hold 2 out, -4. So this one's +4. Now we do chromium. 7 times 2 minus is -14. Hold 2 out, -12. So this has to be +6. Now we can tell. Right, this is oxidation. You went from +4 to +6. So the oxidation step, you see, use this space over here. The oxidation step is SO3 2-.
I also want to know how it's like oxidation. It's also gaining electrons. So wouldn't that be the
This one?
Yeah, because it's going from 4 to 6, so it's gaining. Oh, never mind.
Right. It finally
Whenever it
done.
gets larger, that's how many it's like. It's how many it's like.
Exactly right. So this one is SO4 2-. And I'm going to write the just to keep track of these. And the reduction will be CR207 2-. This is a +6, and that goes to. Let's see. I better spread that out a little bit. We want to need some space in here. To chromium 3+. Okay. Next thing you do, once you've got them separated out, you balance all the elements except for oxygen and hydrogen. So we've got 1 sulfur, that's done. We got 2 chromium and 1 chromium. Okay. So they're balanced. Now we need to balance oxygens. You got 4 on this side and 3 on that side. You balance oxygens with water. We just need 1 water. All right. 1, 2, 3, 4. 1, 2, 3, 4. No, oxygens are equal on both sides. 4 on this side, 4 on that side.
Yeah, but now the left side has a hydrogen.
Then we do the hydrogens, right? So now we've got 2 hydrogens. You balance those with protons. Then we go down here, we got 7 oxygens there.
If you balance them with protons, balance them with protons, is that, that's just the number in front, right? There's a,
Yeah, 2 of them,
okay.
2 hydrogen ions. Yeah. That also means we're balancing an acidic solution. I'll say some more about that in a minute. Okay, so we've got 7 oxygens here. Now we've added 14 hydrogens.
Not as difficult as some of the
Mhm.
equilibrium we had to make.
Okay, once you've got all that done, then you go to the electrons. So we've got this sulfur, that sulfur. We went from +4 to +6. That means we've got 2 electrons there. On this side, we went from +6, 3. So that's 3 electrons added, but they're 2 chromiums. So that's 6 electrons. Okay. Now we reconcile the difference between the two. 2 here, 6 there. This has to be multiplied by 3.
How do you do that? You put it in a bracket. Put it
Uh-huh.
outside.
Like that. So that means we have 3 sulfates,
So you just do a 3 for everything.
3 waters. That's sulfite, excuse me. And 3 times 2 is 6. And 3 times 2 is 6. So now the electrons are the same on both sides. And then when we add them together, they cancel.
Because they're on, okay, I get it.
So now we can put them in the same order as that one. So we've got dichromate. And then 3 sulfites.
You have to.
And then we have water. And then we have 14 hydrogens.
How do you know when to add those? Like put those in the equation? Like where to put them? Is it not in the original? It doesn't matter.
As long as they're on the right side of the arrow. I just put these in first because that's where they were here. And then I fill in the rest of it behind them.
Okay, well, that's what I was meaning, like the ones that weren't originally there, like doesn't matter where they put, where they don't.
No.
So-
It doesn't matter. And then we've got, do this one next. I'm gonna have to move down here. Because I don't want to run off the edge of my screen. We got 3 chromiums, then we got 3 sulfates. Chromium, sulfate, and then we've got 7 waters. Still there, and 6 hydrogens, right? Okay, now we reconcile. We got 3 waters and 7 waters. These 3 go away, and now we're left with 4. Okay,
How are we taking the water away from, okay, never mind, it's going into the product.
yeah, I mean, if we got 3 waters on this side and 7 waters on that side, it's the same thing as saying no waters on this side and 4 on that side. And then the hydrogens, we do the same thing. We got 6 on this side, so now we have 8 on that side.
Like you're using for her.
Right? Because this one's smaller than that one.
It would be the same thing if we did another one, because it'd be negative, okay, I get it.
And then again, all of this is happening in the same vessel. Right? So even though you've got reactants and products, they're all mixed in there together. So the presence of hydrogen ions in this whole situation means this is acidic solution. And that's how you balance, that's where you start to balance all redox equations as acidic solutions. Then if the problem says it's really in basic solution, then you convert it to basic. So in order to do that, I'll go ahead and do it for this one. You just neutralize your hydrogens with hydroxyls. So if we add 8 hydroxyls on this side, right, they go up here, and that makes 8 waters. And then we have to add 8 hydroxyls on this side also, but there are no hydrogens for them to react.
How do you do it's gonna be a
Right, so we're going to have 8 waters on this side and 4 waters on that side. So these waters go away, and now these are 4. So in basic solution, it'll be dichromate, 3 sulfites, four waters yields 2 chromium 3 plus, 3 sulfates, and 8 hydroxyls.
Okay, so you just add OH2.
Uh-huh. Yep. That's what I call the fake acid method. If it says balance it in basic solution, you go acid first, then you convert it to base.
So it's really just gonna be a base.
Yeah, if it's acid solution, you're done. But if it's basic, then you just do that one more step.
But if you make it, it can't be a base now. 'Cause, yeah.
Is that? All right. Oh, subsequent slides are going to go through all this stuff.
Go through quite a few problems.
Acidic solution, okay. Then we've got this final balanced equation. That's what it was before in acidic solution.
Always gonna be acidic, though, right?
Just to begin with, yes.
You have to make it.
Excuse me. So let's move this one. Balance the following in acidic solution. Now, what you want to look for, in most cases, when it says balance acidic solution, do you really need to split it into half reactions? If you've got hydrogen or oxygen floating around here, then yeah, you will have to do half reactions. If there's no oxygen and no hydrogen on either side, then you don't need to do it this way. You can do it by the shortcut method that I'll show you in a minute. But this one, we go through the same procedure, right? This one's a -1, that one's a 0. So it went from -1 to 0. That was oxidized. Bromine ion was oxidized to bromine gas, bromine liquid. And this manganese is, let's see, 7 plus 7. This manganese is 2 plus. It was reduced. So it'd be, this is the reduction, this is the oxidation, and you go through all those steps again, and you end up with that result.
And that's gonna be the hardest part for me, is finding out what the thing is, like how that's 2, you said that was 7.
Yeah. Yeah. Well, just do it on paper then, right? -2 times 4 is -8, right? You have to hold one minus out for that charge. So it's -7 that has to be balanced. -2 times 4. Yeah, that's one of your rules. Oxygen is always -2. And then, of course, the standard elements, those are 0. And that's a -1. And that's a +2. So really, the only one you had to calculate was this one. Then you can figure out which one's reduction, which one's oxidation.
Yeah, because if they have an ion, that's what trouble with that.
And this talks about my fake acid method. And it just tells you to neutralize the hydrogens with hydroxyls. Remember, you got to put them on both sides. Let's see.
Now you know how many hydroxyls they have, it's like equal to the
Same number of hydrogens. What you're doing is
water. Yeah, okay, you're just making water out of it.
yeah. So if you got 3 here, you got to have 3 there. And there's a schematic if you fancy those. So I was just thinking about this possibility. What if we started with hydroxyl instead of hydrogen? You know, instead of doing the fake acid method, what if we started with hydroxyl? What were some potential problems? Well, you'll have to add water to the other side to compensate for the OH. And then balancing both oxygens and hydrogens adds complexity on both sides. It just, the fake acid method is just the least likely to get wrong. Okay, so if we're going to balance this one in basic solution, we've got to do the acids first. And we have to decide which one is oxidized, which one's reduced. We did this one before. This is +7, right? And this one would be +4. This one, we say oxygens -2.
But it has,
And it has, yeah, it has a negative charge. So that contributes +1. But how do we do these? Carbon and nitrogen.
it has a negative charge on the.
Yeah. Right, because we don't have rules for these.
Maybe 0 at first, like the carbon. Because it's metal.
No, carbon's not a metal, but it's in the metal position. Right, it's on the left.
Oh yeah, it's a water solution.
It doesn't show how to do it. Right, that's the trip up, right? You don't know, we don't have rules for these two. I'm inclined to say this is -3. And this one's -3. Nitrogen, since it's in the non-metal side of this combination. That would make this one +2. And that would make this one, see, -5, +4. So in that case, carbon is oxidized and manganese is reduced.
I really not good at that. Taking the numbers up, that's the worst problem.
Well, the first trick is trying to figure out which one's which. Are we going to let nitrogen be the one that varies, or are we going to let carbon be the one that varies? And usually carbon's the one that varies if it's there. So we have to say -3 because nitrogen is 3 steps over. Fluorine -1, oxygen -2, nitrogen -3. This is one of those cases where you're stuck unless you make an assumption. And it's very likely that if we held carbon constant at, I don't know what carbon would be, because it could be +4 or -4, right? It's in the middle. So this is probably the best bet. Say nitrogen -3 and then go with carbon. And from there, if this is -3, then you got to hold 1 minus out for that charge. That means it only has to balance a -2. And this one, you've got a -5, hold 1 out to -4, so that makes this +4. And then go through the step by step. And you should end up with that.
I can do that. The little numbers that you find on top of the thing is what's.
Once you get started, you're okay. Yeah. And it has to be a basic solution. So there are multiple steps here. What's a galvanic cell? Galvanic cell is, well, it honors the Italian Galvani. But a galvanic cell is a battery. It spontaneously produces electric current in an external wire. That changes chemical energy into electrical energy. Right? These redox reactions, if they're all in the same bucket, right? Electrons are transferring, but we don't have access to them. There's no way to get at them. They're moving at the microscopic level. So the galvanic cell is a way of separating the two half reactions so that the electrons can be shunted exterior and we can access the energy that they're delivering. Right, so each one of those half reactions is going to be in a separate physical cell. Then we have to connect them. And the reaction has to be spontaneous. Okay. The reactions that take place in these cells occurs at the electrode. So you got a solution and you got an electrode sticking down in it. A solution and an electrode sticking down in it. And off of that electrode is a wire that goes to the other electrode. And electrons are transferring one way or the other. But when you have the two half reactions, and your electrodes here, you have this external route for them to go, then the electrons could go that way, except one of the rules of electricity is electrons don't move unless they're in a circuit, right? And this is a broken circuit. Right? They don't move from here to here unless you complete the circuit. This is a salt bridge. You need an electrolyte in that salt bridge in order to complete the circuit. Electrons move in this way, the current moves like that. So if you remove the salt bridge, there's nothing's going to happen. No reaction will occur. So for our purposes, we're going to make our salt bridge out of potassium chloride and agar, which is a, have you ever done microbiology? Agar is kind of it's a thickening agent. And you get your nutrient media and you add it to agar when it's hot, and when it solidifies, it makes a gel. And then you can plate your microorganisms on it, your bugs, either on a plate or in a tube. Where we're going to use pure agar with none of that other stuff in it.
Flies get stuck on.
Yeah.
Sit around the house.
And put potassium chloride in it to make the. You have to have mobile electrons, but you don't want the contents of that bridge to mix down here. You just want the ions to move freely. So that's why we embed the potassium chloride in agar. The other way you can do it is to have it set up so you have a porous disc between the two. Then you don't get mixing between them, but the ions can flow freely. And there's one other, you can have this, and you can have a ceramic cup here. Then you can have one electrode here and one electrode there, and you have your different solutions like that. Then the ions can move back and forth this way. I've seen that done also.
I like the porous disc the best.
Yeah, it's cleaner. Now, that's if the electrolyte is different on both sides. If the electrolyte is exactly the same on both sides, then you don't need that. Perfect example is the lead acid battery in the hood of your car. Right? It doesn't have this stuff because the common electrolyte is sulfuric acid. And you have a lead plate and a lead oxide plate. We'll talk about that in a minute. Okay, so there's your salt bridge, porous disc, and all it's good for is to allow ions to move freely and complete the circuit. Okay. This is the, if you draw out the picture of your battery, your galvanic cell, the convention is to put the site of reduction on the right-hand side. So electrons are moving here, and they're going down here, and they're causing reduction. And they're coming from this side, which means oxidation is occurring over here.
How does that one have oxygen?
Huh?
That one has reduction. Oh, that's the agent.
Reducing agent, yeah. The reducing agent is the one that's oxidized. And the names for them are, on this side, we'll call that the cathode. On this side, we'll call it the anode. So the cathode is always the site of reduction.
That means the anode is always oxidation.
Always, yes. Okay. So what do we mean by cell potential? Well, the reaction is spontaneous for a galvanic cell. And when it occurs, it's going to provide a certain amount of push for those electrons moving from the anode to the cathode. And the higher the push, the higher the potential, and that's measured in voltage. And that's what this means. That fancy E is voltage of the cell. I don't know why it came in there. I didn't animate it too well. There we go. The driving force on the electrons is called cell potential, or electromotive force, EMF. And it's always in units of volts or millivolts. The volt stands for 1 joule of work per coulomb of charge transferred. Coulomb is a measure of charge. It's kind of it's inherited from the mid-19th century. So if we're going to make a conversion between Coulomb's charge and actual electrons moving, we need a conversion factor. Oops, I got a video.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
So in order to calculate the potential voltage, the maximum potential that you can expect to get from a combination of 2 cells, because you can have a whole host of different possibilities. we need a standard. Oh, okay, I'm getting ahead of myself. This is actually measuring the voltage. Okay, so you have two ways that you can measure the voltage. One is a voltmeter. A voltmeter draws current through a resistor, and the Ohm's law tells you what you should get from a certain voltage and a resistance and a current. And the electronics in the voltmeter interpret that. The problem with a voltmeter is it doesn't give you the maximum that you can have. The maximum voltage that you can get from a reaction is one in which the electrons don't move. You just measure the push, you don't move. When they start moving, then they develop some what they call internal resistance. And that reduces the voltage that you get. So the maximum voltage, you need another way of determining that. So the maximum self-potential requires that you have no current. Electrons are not moving. But you can still measure the push by opposing. You set up the in a device called potentiometer. You have a variable voltage that is calibrated, and you oppose the voltage of the reaction until the current stops. And then you measure how much voltage that put against it. That gives you the maximum voltage for that cell. But they're much more expensive. So most of the time, multimeters will just have voltmeters. And in most cases, that's all you need. Okay. Okay, all right. Now we're at the point where you can calculate what your expected voltage is for a given galvanic cell. And in order to do that, you need some standard measure for each of the half cells, right? How much voltage can you expect from this one? How much can you expect from that one? And then you combine them to give you your total for the cell. Well, the problem is half cells don't exist and can't produce voltage on their own. They've got to be compared against something. So we have a standard cell. And under standard conditions, E0 are measured for each of the cells against a standard half cell at 1 molar concentration, and if there are any gases present, at 1 atmosphere pressure. That standard cell is the standard hydrogen electrode. Here. The standard hydrogen electrode on its side is set arbitrarily at 0 volts. So anything you measure against a standard hydrogen electrode is attributed to the other cell. Okay, and those values have all been compiled for us and put in tables. And then what you do is you compare, if you want to combine this half cell with that half cell, you have voltages assigned to them that you can combine in the correct way and determine what's the maximum I can expect from this reaction. And these tables are always set up as reduction potentials. So it'll be some ion plus electrons, but it doesn't have to be an ion. It's the reactant plus electrons yield something. So the electrons are always on the left-hand side. They're always reduction potentials. So some of them will be positive, some of them will be negative. Okay. One thing we need to know also is, what do we do with the value for the voltage if we have to use the reaction in the reverse direction, right? Because you can't put two cells together and both of them be reduction potentials. One of them has to be oxidation. So if you have to flip one of them and make it oxidation, you just change the sign on the voltage. So if the voltage is like minus 0.5 volts. As a reduction, then as an oxidation, it will be plus 0.5 volts. So what happens to the voltage if the half reaction has to be multiplied by some constant value? Nothing. Nothing happens. E0 is an intensive property. It doesn't change with amount. So if you're going to combine two half reactions and make an overall reaction, but one of them has to be multiplied by a constant, then it doesn't affect the E0 at all. It doesn't affect the half cell potential at all. Okay. Now, I mentioned spontaneous direction. Galvanic cell will run spontaneously. How do we know? What voltage does it produce? If the voltage of the two combined cells is calculated as a positive value, then the way you have it set up is spontaneous. But if you reverse them both and you put them in the wrong place, right? You put the anode in the cathode the anode, and calculate the voltage again and get a negative, that's not spontaneous. The E value must be positive for a spontaneous galvanic cell. I got these out of my textbook. You probably got a similar one in your textbook. And this shows that they're all reduction potentials, right? The electrons are all on the left-hand side of the arrow. So for this reaction is 2.87 positive volts. So if we combine these first two, right, they're both reduction now. One of them has to be oxidation. So which one would be oxidation and still give you a positive value? You would take this one and flip it and make that negative. Then when you subtract that from that, you still get a positive value. So this would be the reduction cathode. This would be the anode. Flipped. And generally speaking, that's the way you'll always have to do it. The way the table is set up, if you've got two half cells anywhere in here that you want to combine, the one below is going to be the anode, and it has to be flipped in order to give you a positive value. There's some more half reactions, and you've got voltages. They start from high and go to low. And eventually we'll get down to this one. There's your standard hydrogen electrode. It's at 0. You can make a cell with any one of these as the standard hydrogen electrode if you want to. So now below this, we're getting into negative territory. So against this standard hydrogen electrode, anything above it, this one is the anode. Yeah, you would have to flip this one for these. But for anything below it, this becomes the cathode. And these are the anode. So they would go backwards. Iron would be oxidized to produce iron 3+ against this electrode. Excuse me. Okay, your textbook probably takes the same approach. But once you identify the cathode, the anode, you just take the actual value for the reduction potential for the anode and change the sign. That's all that means. Okay. That's nothing new. That's nothing new. I told you that already. Okay, how about this example? This is the overall reaction. So we got to decide what? half reactions. Okay. So the reduction potential from 3 plus to 2 plus here is 0.77 volts. The reduction potential for copper, 2 plus and copper here, is the wrong direction, right? Because copper needs to be on this side. So if we write it this way and then change that one, flip this one to a negative, then when we combine this one and this one, we still get a positive value. So this, the way this is written, that is spontaneous. If we flip this one instead, we'd end up negative. And then it'd be the wrong direction. Now, it's also, we also need to know how many electrons are transferred. The reason is, these are all standard potentials. Everything's 1 molar concentration at 25 degrees Celsius. But most batteries are not 1 molar. So we need a way to calculate the actual voltage when the concentrations change, right? And for that, we'll talk about it in a minute. It's called the Nernst Equation. But in order to do that, we need to know how many electrons were transferred in this balanced equation. And to go from here to here, we add 1 electron. To go from here to here, we lose 2 electrons. So this needs to be 2 and 2, and 2 electrons were actually transferred. 2 moles of electrons in that reaction. So we need to keep track of our number of electrons transferred for later calculations. Right. This is going to be the cathode reduction, and this is the anode. That's the balanced reaction there. And the cell potential is going to be 0.43 volts. The standard potential. Okay. This refers to the actual cell voltage, the E with no little zero by it. And for that, we need, okay, there are 2 reasons for knowing the number of electrons transferred. One is to calculate the actual cell voltage. The other is for electrolysis. We haven't talked about that yet. Electrolysis is you take the reaction in its spontaneous form and you run it backwards. Because if we want to, let's go back. Oops, wrong way. Oh, here it is, right here. Spontaneously, copper will be oxidized. But suppose we want to precipitate out copper, or we want to plate out copper on an electrode. What we need is to apply a voltage in reverse greater than this voltage. If we do that, we'll run the reaction backwards. That's electrolysis. And if you do that, you'll convert the copper ions into copper metal. We do that all the time. We plate things like bumpers. Well, not anymore, but on vintage cars, we still chrome plate bumpers by running the reaction in the non-spontaneous direction. Okay, so that's why we need to know how many electrons are transferred in the reaction, because the stoichiometry will tell us how much voltage we need for how long a time to get the amount of plating of the metal that we want. And I think we'll do a calculation like that in a minute. All right, this one's a little bit tricky. Okay. The strongest to weakest oxidizing agent. Remember, the oxidizing agent is the one that is reduced. So we're going to reduce this one, add electron, add electron, add electron, add electron, add electron. We're going to reduce those to be oxidizing agents. So we don't know reduction potentials for sodium, fluorine, and iron. We do have them for the sodium ion and the fluorine molecule and the iron 3+. Right, so that's where we're starting. We have each of these reduction potentials, and we've got iron, sodium, let's see. There's iron, there's sodium, there's fluorine, there's sodium ion, so we've got sodium in two places, and we got chlorine here. But if we want to rate them as which is the most easily reduced, oxidizing agent, which is the most easily reduced, then we have to compare these values. Right, if we're talking about fluorine with 1- charge, then we really need this one, right? What's the voltage on that? That doesn't make any sense at all. Right, so that's unknown. This is unknown. That's known. We just had to go back. There we go. Oh, that didn't change at all. And then this one is kind of odd, right? Because metals don't like to acquire electrons. So what we're saying is the least likely to be reduced is sodium. The next least likely is iron. Right? Then sodium ion, we can add electrons. We have this value here. The most active is the most positive. So we've still got this one to do. And so if it's already got a charge on it, it's not going to accept another electron. So it's the least likely. Sodium is the next least likely, so forth. So the logic there is kind of difficult to follow. In fact, that's probably not a good question. Hopefully it will spark some thought, but it won't give you any good answers. Okay, instead of drawing out the whole picture of this cell and that cell, we've got a shorthand notation called line notation. And the line notation is set up so just like the cell is. So the anode for the line notation is on the left-hand side, cathode is on the right-hand side when we write it out. The divider between the two cells is a vertical double line. That indicates a salt bridge. A single vertical line is placed in there if there is a phase difference anywhere in the reaction medium. So if we have a solid electrode into a liquid, then we'll put the solid here, then we'll put a vertical line, and then we'll put the liquid components here, then a double line for the bar for the salt bridge, and then we'll put the rest of it for the cathode. It's also a good idea to put the concentrations, if you know them, for the solutions. So here's an example. This is the anode, right? Magnesium is oxidized to magnesium 2+, gives up electrons, and it delivers them through an external circuit here, like that. So when this happens, those electrons go out here to the cathode. Oops, that's not exactly right. Well, yeah, it is. Okay, it is. Now that I think about it, it's delivered through the electrode and causes reduction at the electrode. Actually, this would be more accurate. Right there, at the phase change. So this one actually should be right here. Right there. Electrons are transferred like that. Okay, there's the anode, there's the cathode, and that's our line notation. Now, if there's no phase difference between the two, then you may have a salt bridge, and then maybe on this side you'll have let's see, was it oxidized or reduced? It was reduced, so it'd have to be on this side. Like that, because there's no phase difference between these two for the reaction. And the electrons will come in here and reduce this one to that. Actually, probably should be the other way around. Anyway, the point is, if there's no phase difference, you don't put a vertical line. Sometimes, and if the reaction is entirely in the electrolyte, then you need a way to get the electrons in there or out of it. And for that, we use an inert material. Carbon, graphite rod, or platinum. And if that's the case, then you draw the vertical line, you write carbon or platinum with a phase difference between the rest of the reaction. Let's see, do I have an example? No, no. So, describe completely the galvanic cell based on the following half reactions under standard conditions. Okay, so we got reduction here, reduction here. One of them is going to have to be flipped. If we don't have our table, we can't tell which one's above and which one's below. We look at these values. Which one can we flip? Both of them are positive. Which one can we make negative and still have a positive summation? This one. So that one will have to be the anode. And this is the cathode. So if we make that one negative, we don't get much of a voltage out of it. Get it? Right. 0.03 of a volt. And then if we balance the equation, it looks like 1 electron here, 1 electron here. So only 1 electron was transferred. Okay. Let's see. That's nothing special. This is the way we would draw it out. Picture form. We're going to have line notation. For the iron, the electrode is not part of the reaction, so it needs to be some inert material, right? And the electrons flow out of here and over here, and silver then is plated out on this electrode. Oh, and in this situation, we should have some counter ions. That just means if this was positive, there needs to be a negative in there somewhere. So it's not going to be chloride because that's not soluble. Probably nitrate would be a good one. And for this side, we can make it nitrate too. I wouldn't make it chloride either because you'll get some chloride migration and that'll precipitate out your silver. So nitrate on both of them would balance these positives. Line notation, okay? So there's your platinum, and there's the iron oxidized to iron 3+ with a comma instead. They're in the same phase. There's your salt bridge, or porous disk, and then your silver is reduced to, silver ion is reduced to silver metal. Okay. Designate the anode cathode in such a way that the direction of electron flow gives a positive E0 for the set. Okay. And then balance the cell reactions so that you can figure out how many electrons are transferred. Okay. So what are we doing here? Sketch a diagram, show the direction of flow, and label everything. So if we have a silver electrode and silver solution at 1 molar and copper ions at 1, what you need is to know the voltage. And is that given? Not given. You have to look up the voltage and find out which one's which. It turns out that the silver is going to be in the cathode and the copper is going to be in the anode. And you have to compare, or we did that earlier, didn't we? No, that was for iron. Okay, so you have to look up the values and see which one's going to be the anode, which one's cathode. I must have done that in order to set it up this way. Okay. This is not the end of it, is it? Concept check. What would happen to the potential if you increase the copper concentration? Let's see, increase the copper concentration. Well, what reaction is going on here? Oh, here we go. This is the reaction at the anode. If we increase the copper concentration, the copper ion concentration, the equilibrium goes that way. So that would make the electrons go back this way and reduce the flow of electrons, decrease the voltage. In that case, the copper 2+ reduction potential will increase. Yeah, we would increase the reduction potential, but when we change the sign, that would decrease the overall voltage. Because we would make this one bigger as a negative, and that would make that one smaller. Okay, so if we're going to get any useful work out of this spontaneous reaction, we need to understand what that means. What is the relationship between cell potential and work? Well, first of all, they're going to be opposite signs. Remember when I said potential is the amount of work done per coulomb, so joules per coulomb. But work is always in reference to the system. What's happening to the system? Well, if it's losing, I mean, if the system is doing work, that means W is negative. But it's not spontaneous unless E is positive. So we have to give it a negative sign to to fudge the signs, to make them compatible with one another. Okay, then if we solve for W, a minus W is E times Q. So the coulombs, or the charge, times the voltage is equal to the work. And this is the maximum amount of work that you can get out of that system, is minus the Coulomb charge moved times the voltage, maximum voltage. Okay, that just gives you the units. Work is in joules, charge is in coulombs, and if that's the case, then the potential is in voltage, in volts. Okay. The actual work that's realized is always less than the calculated maximum. We learned that from entropy. There's always loss. Okay, here's our conversion. If you've got a stoichiometric relationship, a balanced equation, and you want to determine what's the charge that is associated with the movement of so many moles of electrons, then here's the relationship. 1 Faraday equals 96,485 coulombs per mole of electrons. So there's your equality, and you can use that to convert from one to the other. Okay. Now, we also know that the maximum amount of work is equal to the change in free energy. We figured that one out in the last chapter. So for a galvanic cell, the maximum amount of work equals delta G. Delta G is equal to negative QE. And since the charge in coulombs is equal to the number of moles of electrons times the Faraday, then you can substitute this into that Q. Here we go. So the delta G is equal to negative moles of electrons times the Faraday value times voltage. And that will give you delta G. And we also know that spontaneous reactions require a negative delta G. So if this is a positive, then that makes this negative, and we're good. Oh, there's Michael Faraday when he was young.
Faraday cake.
Yeah, yeah. Or somebody did name it after him. But he probably did invent it. The stories that they tell about him in the research that he did, he was a master craftsman in the laboratory. He could figure out ways to do experiments that you couldn't fathom. And they were so simple. They get the results. They answer the questions with the simplest devices. Okay, so this maximum cell potential is related to the free energy, difference between the reactants and the products. All right, so there's your value. The galvanic cell will run in the direction that provides a positive E value and a negative delta G. That's spontaneous. Okay. Up to this point, we've combined half cells with different materials in each one. But we can produce a galvanic cell with exactly the same chemistry in each half cell. The only difference is one's at a different concentration than the other one. So how do we do that? Well, we're looking at Le Chatelier here. Electrodes are the same material. The solution concentrations are different. The lower concentration will increase and the higher concentration will decrease. They're trying to reach middle ground. So this one's going to decrease the number of silver ions, which means they're plating out on that electrode. And this one is going to consume that electrode and send electrons up here. So the high concentration is the cathode, low concentration is the anode. We're going to make one of those next week. We're not going to use silver. We're going to use copper for the concentration. We'll use copper and zinc for one experiment. Yeah, and then copper, different concentrations for the other one. Here he is, Walter Hermann Nernst, German chemist.
He almost lived 100 years.
Huh?
He almost lived 100 years. He was only about 20 off.
Yeah, it's like, let's see, 36 to the turn of the century, and then 41 more, 77. Yeah, he had passed June, so he was 77, going on 78. So he was active in thermodynamics in particular, and electrochemistry.
He lived in 3 different centuries.
Yeah. He the third law of thermodynamics, he didn't invent it, but his work, the Nernst thermal equation, led others to propose the third law of thermodynamics.
Okay, so they basically took his work and said, all right, this is what we're going to say.
This is what it makes. This, because his work was verified, then now they can make the next jump to third law. Right, perfect crystal at 0 K has no entropy.
That's the only thing I memorized for that third law was the crystal.
Yeah.
Crystal at 0 K was what I memorized.
And he got a Nobel Prize for his work too. Okay, so the Nernst equation is what we need. His work on electrochemistry allows us to calculate the actual voltage for a galvanic cell at non-standard concentrations. Actually, non-standard concentrations and temperatures, but we're going to simplify it. This is the Nernst equation in its most versatile form. Right, the actual voltage is the standard voltage minus gas constant times temperature in Kelvin divided by moles of electrons divided by the Faraday times the natural log of Q. So you need to know the concentrations, you need to know the balanced equation to calculate Q. But under most conditions, we're going to have, here we go. Temperature is going to be 25 degrees in most cases. And we'd rather use a common log than the natural log. So we do these transformations, right? We insert this temperature for a standard, for 25 degrees Celsius. And we make this conversion for the natural log, 2.3026 times the common log is equal to the natural log. So this value is blended into that value. And we come out with 0.0591 divided by the number of moles of electrons times the common log of Q. And that's the one that we prefer to use. It's just easier to handle. And this is just a proof for that equivalence of natural log and common log, in case you're interested. But it's not something you're going to see on a test. Okay, so at 25 C and equilibrium, Q is equal to K. And once you reach equilibrium, there's no voltage. Okay? So when that happens, we can say, all right, so under these circumstances, must be on a timer. This Q, this equation, then, if we substitute K in here, that means no voltage. But there's still the standard voltage. So now all we have to do is for this equation, all we need to know is what is the standard voltage for the reaction, for the cell, how many electrons are transferred, and we can calculate K for that reaction. Okay. For this reaction, we divide the, we have to calculate the sulfur oxidation states to be sure that this one, well, actually, if we want to know the standard voltage, all we need to do is say which one's which. We just say this one is going to make that, and this one's going to make that. Then we go to our table and look up these values and say, all right, which way is it going? Right? If we leave it the way it is, we get negative. So what we're going to have to do is convert this one to the anode. That makes it positive. Then we can add it together, and that gives us a positive E0. But if we want to calculate E, if we want to deal with K, we need to know how many electrons were transferred. So we got to figure that out. Right, we have to reverse the second reaction. Okay, that gives us E0 is here. That's good. 2 moles of electrons are transferred. How do we know that? Because we have to multiply this one by 2. Right. This reaction, this reduction requires 2 electrons. So this one has to be multiplied by 2. So now we know that we have 2 electrons transferred. So N equals 2, got that nailed down. N equals 2. Here's the standard voltage. We rearrange the equation in favor of K. So now we substitute E0 in here. We got that one is constant, and we got the 2 here. So now we know that the law of K for this reaction is 22.6. Really, really big number. And that's common for redox reactions that are written in the spontaneous direction. The K is going to be huge. Oh, excuse me. We're not done yet. That's the law of K. I'm sorry. So we have to take the anti-log of 22.6. That's even better. 4 times 10 to the 22nd is the K for that reaction. It's massive. Yeah. Okay. What's the difference between E and E0 when is E equal to 0? At equilibrium. At equilibrium, the battery is dead. Yeah, the battery is dead at equilibrium. Okay. When is E0 equal to 0? For a concentration cell. Because E0 is 1 molar concentration for both cells. So if they're both the same concentration, E0 is 0. Yeah. Okay. A concentration cell is constructed using 2 nickel electrodes with nickel 2+ concentrations, 1 molar on the cathode side and 10 to the -4th molar on the anode side. So what's the potential for these two? All right. So I've used subscripts here for the cathode side and anode side and written it out that way. So in that case, here's our operative equation because Q, we're not at equilibrium, so there's a Q value here. Then we have how many electrons transferred to. Our E0 is 0. So, and then the Q is calculated from the actual concentrations. Because if we write it out this way, that's a solid, that's a solid. So we only have this one divided by that one. Okay, that's what the Q is here. And then when we calculate that, it turns out it's only 0.118 volts. Actually, that's not bad. It's really a pretty good voltage. The one we're going to construct, we expect a voltage in the millivolt range.
So if you stick your finger in it, you feel a little part.
You feel nothing. Maybe put your tongue on it, a little more sensitive.
Yeah, my brother got the battery. He didn't, man, he wasn't happy afterwards.
A 9-volt battery.
I don't know, it was one, but he wanted to see if it still had a charge.
Uh-huh.
But he didn't really want to stick a stent to it, but there wasn't no other way really at the moment, so he just, yeah, it's charged.
Yeah, those 9-volt batteries can kick. It'd be kind of hard to do any other kind of battery because the electrodes are on the opposite sides.
Yeah.
So the 9-volt, it'd have to be that
I don't know, we can do it to regular batteries if you do it right. You just have to be really sensitive.
one. Oh, put it in your mouth upside down like that, so it's touching top and bottom.
You just touch the fingers time. I don't know. Some people probably can't do it because of the way their body's made.
Yeah. Okay, let's say you make a galvanic cell at 25 degrees containing a nickel electrode at 1 molar with this standard potential and a silver electrode at 1 molar with this standard potential. Sketch the cell, label anode, cathode, direction of electron flow, and cell potential. So that's what we're going to do. This is the line notation. So we have to decide, is this really the anode? Is the nickel being oxidized? Well, let's see. If we make this one negative as the anode, that won't work. So this one has to be flipped. All right, so that's right. This is the anode, this is the cathode. And the anode then is on this side, the cathode's on this side, the anode's on that side. And the total voltage will be 1 volt, 1.03 volts. With 2 electrons. We have to multiply this one by 2. 2 electrons moving.
Now we get the batteries.
Yeah. Okay, so here's the lead acid battery under your hood. This only shows 2 cells, it looks like. 1, actually 3. And what I was saying earlier is, since the electrolyte is the same for both cells, there's no divider. You just dunk them both in the same electrolyte. This is the overall reaction. So they're both this lead and that lead, which are different oxidation states. Right? This is 0, and this is +4. Right? Because 2 oxygens makes -4, lead has to be a +4. On this side, they're both +2 because sulfate is 2-. So this lead is going to that lead as an oxidation. That's the anode. And this lead is going to that lead as the reduction. That's the cathode. So which one is which? This is the lead oxide, and this is the lead. So this is the cathode, that's the anode. Excuse me, the other way around. I'm sorry.
Can you touch by looking at the front? Because that one looks like it's been ate off of.
Yeah, plus it shows you the flow of electrons. It's coming from this one. This is the anode going to the cathode. Yeah. So how do we get 12 volts out of this battery? Well, we don't know what's the potential here. We'd have to look it up. I know what it is. The potential for each one of those cells is 2 volts. So to get 12 volts, you put 6 of them in series. That's one of Kirchhoff's laws in physics. If you put them in series, then they push with each other. And 6 of them pushing at 2 volts each gives you 12 volts total. So when you look at your the top of your battery, I don't know, you may not be able to see it anymore, but it used to be you had 6 holes in the top of your battery, and each one of those cells was separated by a plastic divider. Right? So you had separate cells in here. And then they were connected in series to give you your 12 volts. And that's standard for any battery. So if you get your standard dry cell battery is 1.5 volts. That's one cell. Dry cell battery, there you go. See, it's only got one cell, and it only puts out 1.5 volts. So the difference between a D cell, C cell, AA's, and AAA's is just the size of the battery. They all make the same voltage. So the D cell is going to last longer.
Battery size.
Well, because you can't fit a D cell inside that.
Make them bigger.
So let's look. Here's the manganese oxide and ammonium chloride cell. This graphite rod is simply a conductor of electrons. It does not participate in the reaction. But the casing here, this zinc casing is the anode. So that zinc casing is going to be eroded. And the zinc ions are going to move into this paste, and electrons are going to go, electrons are going to go out here, at the bottom. They'll go out and they'll come back in the top here. And the reduction takes place here at the surface of the carbon electrode and this manganese oxide paste.
I hate this kind of batteries that comes up next.
You hate them for what?
The ones that comes up next because I never could find them whenever I needed them when I was little, because I had these little toys when I was little. I couldn't find those.
Oh, okay.
Whenever you drop them. They're so tiny.
You're probably, and you're probably not going to find this particular one anywhere because it's got mercury in it.
Yeah, no, I saw mercury and I was like, I think that's kind, but it was like that shape and that small.
Now they use silver.
Yeah.
And
I see them all over the place now when I was little.
yeah, because there are lots of hearing aids out there too.
Yeah.
All right, this is a fuel cell. It's kind of like a battery, but the reactants are continuously renewed, which means it'll run indefinitely as long as you've got enough fuel going in. You got oxygen going on one side, hydrogen going in the other. This is one type of fuel cell. There are a whole host of different types, but this is the kind that was used on the. Yeah, no, they used fuel cells in spacecraft during the Mercury, Gemini, and Apollo missions because they had tanks of hydrogen for their rockets and they had oxygen for breathing. Yeah, it's the one that blew up for Apollo 13. So they got plenty of oxygen and plenty of hydrogen. They just used the fuel cells to generate electricity. And this tells you which one's which. The one where the oxygen comes in is the cathode. Right? Oxygen is reduced from 0 to -2. And hydrogen is oxidized from 0 to +1 for the anode. The problem with fuel cells for the longest time is they have to be run at extremely high temperatures. And that's not practical for automobiles. The temperatures come down over time with developments, but they're still a little bit impractical. Plus, we don't have the infrastructure for it. You need the filler stations.
Yeah.
And with the push now for total electric vehicles, Yeah, I think it is too. What we need is, if we're going to do something like that, we need to find out what fuel do we need, because oxygen's everywhere. So the fuel is the thing. And there are fuel cells that were developed based upon methane.
What are they trying to use in what is the fuel for the electric vehicles? Just electric?
Electricity, that's it. They're batteries.
I don't have their own.
No, I think the maximum they go like 250 miles on a good day. No, no. Just think what's going to cost you when you have to replace the battery.
Yeah.
Like $7,000-8,000.
They're gonna make one that absorbs the sun's energy.
Do what?
They're gonna make one that's solar.
Well, they already have experimentally.
If that works, that would be decent, as long as they can hold the solar energy from it.
Problem with solar is the energy concentration is too diffuse. Yeah, you got clouds,
Yeah.
but even in full sun, it doesn't produce much voltage.
As long as it can charge enough and stay in it long enough, it would be a good energy source. Like for a vehicle anyway.
What they need is nuclear. I
For a
mean,
vehicle?
yeah.
It would be dangerous.
No, they just, they could build safety into it, make it a thermoelectric.
We have a shootout with a person in a vehicle, what's the engine? Just with a middle.
Oh, yeah, we have a hazmat situation.
Yeah.
Okay, now, I think this is the last topic, corrosion. What is corrosion? Basically what it is when we smelt ores to make metal, we're reducing the metal ions in the ore to metal.
Making them more compact too. Maybe.
Well, yeah, that too, because you're getting rid of the oxygen and sulfur and other things that are combined with it. Yeah. But what they're trying to do is they're trying to go back to their original state. That's corrosion.
Corrosion's going back to it.
Yeah. Oxygen, sulfur are the two most common reactants for the pure metal. This is a schematic of what happens when a water droplet hits an unprotected iron surface. It sets up a galvanic cell across that drop. So here's the anodic region where you get oxidation, and here's the cathodic region. Cathodic area. Electrons are transferred out of this region in that direction and produces rust. The problem with iron and rust is also a problem with density. The density of iron oxide is much, much less than iron. So when it starts to form, it expands and it cracks the surface and makes more of it available. So once it gets started, it just steamrolls. Yeah.
If we were to smelt down a bone, what would the pure thing be? Would it be calcium?
A bone? Largely calcium. Yeah. Okay, how do we prevent corrosion? One way is with coatings. We can paint it, right? Keep the oxygen out of it, keep the water out of it.
That's why you paint the wood whenever you make a porch.
Well, that would protect the nails.
Yeah, but it doesn't rot.
Yeah, but that's not corrosion.
It won't be rot.
No, that's not corrosion. You could stretch the understanding because most biochemical reactions are redox reactions. Yeah. Okay, so I'll go with that.
I'm just thinking that since it's like, I don't know, to me it just fell in the category.
You can also plate the metal with some other metal that's more reactive than the metal underneath.
See, we play, I forget what metal, but we play with like silver sometimes, and iron.
Yeah. You ever heard of galvanized buckets? Your grandparents should have one laying around. You just take molten zinc.
You got a wheelbarrow?
Yeah, molten zinc and dump your steel bucket in it and let it harden. That coats it with zinc, and now it won't rust.
We got a plastic one that's been around since I was a little baby, and I don't know how it's still around.
Yeah. You can also combine the more active metal with the other metal alloys. That's stainless steel. It's got chromium in it.
Yeah.
The chromium is so much more reactive than iron that if the surface of the metal is instantly converted from chrome to chromium oxide.
Stainless steel.
Oh, no, you can, we used to have stainless steel countertops in my lab with the Department of Agriculture. And it would corrode because we had this big tank of hydrochloric acid we used to clean things with. And chlorine is murder on stainless steel.
I have a knife with stainless steel, and I was wheeling, and it stained it the color of wood or the ranch or something.
Uh-huh.
And I tried to clean it. I was like, so much for being stained.
Yeah.
I was so annoyed.
There are good stainless steels and there are bad stainless steel. If you buy a cheap stainless steel, it won't last. It won't stay sharp.
I don't think I have a small sharp knife. I don't have one that's brand new, but I ain't gonna use it.
I've got one knife. It's a hunting knife, a buck.
Yeah.
And I sharpened it 10 years ago. I pull it out, it'll still shave hair.
My brother had a knife once. He went like this to show how sharp it was. His arm was bald for the rest for a while because it's just a big old pile of hair down here.
Yeah.
I said, "You have a sharp knife." He said, "Yeah."
It's an art. The other way that you can protect the metal is you create an artificial galvanic cell, cathodic protection. So what you do is you connect the metal through a wire to another metal that's more reactive, and it acts as an anode and delivers electrons through that wire to the metal you want to protect and keeps it reduced. They use that on fuel tanks and pipelines.
It's like center reinforcements.
They still do that on ocean-going vessels, which have steel hulls. They strap zinc around the bottom, all the way around the bottom of the hull, below the waterline.
I just kept that on making water pedals.
Do what?
Like I've heard of them making like highways under the water, like the roads across the ocean.
The longest one I know of is across the English Channel.
Yeah.
The Channel.
But it's basically just gonna be like glass. Like it goes around. I was like, I ain't gonna go through that.
Oh, you're talking about like across the Atlantic Ocean?
Something like that. I thought I read people planning about it, like just making a big old glass tunnel that you can drive through, where you can see the ocean through the glass. And I was like, I'm not gonna go through that.
No, not at 2 miles down.
I wouldn't even go like a mile or less.
No.
That big would just sink, and you wouldn't be able to get out because of pressure.
Yeah, all you need is somebody to have a traffic accident down there.
Yeah. And even if they made it sturdy enough, like if they said they would, I still wouldn't.
No.
Because there could be like a shark or something, just be stubborn and just keep on hitting it or something. They can do that sometimes.
Well, it's across the Atlantic Ocean. It's got to cross the Mid-Atlantic Ridge, and that's volcanically active.
Yeah.
I mean, all they need is just one eruption, and that's all she wrote.
Just one tsunami or earthquake would probably break it.
Yeah. So this is an example for magnesium is anode and the iron pipe is cathode, and this corrodes and sends its electrons in here and protects it. Some metals protect themselves by rapidly corroding on the surface, and when they do that, they eliminate access underneath.
Yeah.
That's why aluminum lasts so long in the environment. It's a very reactive metal, but that protects it. So you throw a can out in 100 years, it's still there.
Yeah. There's some that's like only half the people who own the land where I'm at now. That was before even my parents were born, and they're both in their 60s, almost 70. And I go out in the hills, and there's a very, very old can sitting there. And it's just like that for the rest of I'm just saying, like, how old is this?
Yeah. Okay, so we've already mentioned those things.
I think we should just go on to page 50.
Electrolysis. I mentioned this one earlier. The types of problems relate to running a spontaneous reaction in reverse. That's the whole deal. So in this case, we're electrolyzing water to make hydrogen and oxygen. The spontaneous direction would be space shuttle engines, rocket engines, where you put hydrogen and oxygen together and make water. If we run a direct current through water, we will we'll reduce the hydrogen and oxidize the.
Yeah, I think just like heating it up.
Huh?
And then just basically heating it up to like make it steam and make it get those two.
There are a number of ways to do it. I mean, in the laboratory setting, I always use a direct current. And the one electrode produces oxygen, the other one produces hydrogen. You can also get hydrogen produced when you run the alternator in your car. You get your engine started and you've used some of the energy out of your battery. The alternator puts it back. It drives the reaction in reverse. The problem is if your circuitry is not set up right, or if it's faulty, it may let you overcharge the battery. And when you overcharge, it does this reaction to the aqueous solution and produces hydrogen gas that builds up in your battery. Nowadays, that's not such a big problem because we have one-way valves built into them that lets the hydrogen escape before it has a chance to build up.
My old truck, we used to put the battery for my truck in my old one. There's a little bucket like built inside of my truck. You place the battery inside, and I've never seen that before.
Oh, plastic bucket.
Yeah. I've never seen that before in a vehicle, but you just like sit inside. Man.
Instead of just a tray.
Yeah.
Okay, if we want to do some stoichiometry with electrolysis, what we really need to do is know how long are we going to run the current at what amperage. If you've never had physics, I better explain what an amp is.
No, I have that next semester.
An amp, abbreviated A, is equal to 1 coulomb per second. So past this one point, if you measure a coulomb of charge in 1 second, that's an amp.
This physics is going to be hard.
There's lots of math.
No, I'm not going to like physics.
Oh, you don't like
I
math?
hate it.
Okay.
I've
Well-
never worked so good. It's so fun.
All I can say is knuckle down and learn.
I dropped trigonometry because I.
Really?
Yeah, I had to pick it up again, but I dropped it for this semester. I didn't want to go.
Well, maybe your brain wasn't ready right at that time.
Oh, statistics, I have a C. That or a B, I don't know.
So this procedure, in order to find out how many grams of copper is going to be plated out, you need to know the balanced equation and how many electrons are being transferred. Once you know that, then you can calculate how many grams of the metal are going to be plated out. Oh, here it is. Amps is coulombs per second. So you multiply that times how many seconds, that tells you how many coulombs of charge. And then you make the coulomb conversion with the Faraday constant to know how many moles of electrons. And then that goes into your stoichiometry. Okay. An unknown metal is electrolyzed. It took 52.8 seconds for a current of 2 amps to plate out 0.0719 grams of the metal from a solution containing the metal and 3 nitrates. So that metal is a 3+ charge. Because that's a -1 charge, the 3 of them, that has to be 3+. That's important. So there we have 52 seconds of that current. So we need the moles. How many moles of this were plated out? If we know the moles of that, we got the grams. Then we can calculate the molar mass and determine what the metal is. Okay. So here it all is in one big splash. All right, here's the balanced equation. This is actually the important equation, right? 3 plus for that metal plus 3 electrons yields the metal. So if we've got 2 amps going through for 52 seconds, that's this is how many coulombs it is. This converts the coulombs to moles of electrons. And with 3 moles of electrons per mole of metal, that tells us how many moles of metal there are. And then once we know how many moles of metal, we can grams per mole. So this is the molar mass, 197 grams per mole. Look it up on your periodic chart. That's gold.
In my head, I was like, AU, that's not gold, AG is. And now
No, that's AG is silver for the Latin argentum.
Yeah. I knew that AU was gold because I looked at it whenever I was looking at this earlier. I was like, that's gold. In my head was like, no, it's silver.
Are you having an argument with yourself?
Because I know AG and AU because I was writing a story once and I was using silver as a thing, so I knew for a fact that silver was AG. I don't know why.
Okay. Here's another use of the information that we've accumulated so far. If we have a solution that we know is 0.1 molar in each one of these metals, predict the order in which the metals play out as the voltage is brought up from 0 and it gets higher and higher and higher. Okay. First of all, where are the metals going to play out? Well, you're going to have to reduce them, right? So they're going to play out at the cathode. Yeah. Right. That's the site of reduction is the cathode. So we got to add electrons to each one and make the metal. So that means they're all coming out at the cathode. Even though this reaction is going to be forced in reverse, by definition, it's still the cathode. Yep. Okay, so we take the reduction potentials, and that will predict the order of plating. So the more positive the standard reduction potential plates out first as the voltage is increased. Okay, here we go. So the copper is at 0.16 is the most positive, it'll plate first. Yeah, and then this one is less than that one. And then 10 is less than this one. Right? The reason being, as you drive electrons through there under voltage, it's got to oppose a higher and higher. It's got to switch that one. It's got to oppose that voltage. So the more positive is the more spontaneous. Right, it takes a lot for zinc. What that means is, from an economic standpoint, it's cheaper to plate copper than any of them. Production of aluminum. When aluminum was first purified and converted to metal, it was done chemically. It was extremely expensive. So the King of France would entertain his guests with aluminum silverware, not gold. Gold was a lot cheaper to produce than aluminum.
Probably everywhere at that point.
Yeah, I mean, especially if you're the King of France, it's no shortage there.
Well, they use coins like gold coins.
Okay, so we can produce aluminum, purify metals, pure copper. In order for copper to be useful as a conductor, it needs to be 99.99% pure. The smelter produces maybe 95%. And then they send it off to a secondary process, and they use electrolysis to purify it further. Yeah. Metal plating is another option. Electrolysis, yeah.
Silver is like more conductive than copper is. If you get it.
Yes, it is the most conductive metal, silver. That's why when you build your computer and you put your CPU down on the heat exchanger, well, the heat exchanger on the CPU, you have a silver paste that you put on that surface, and then you put the cooling unit on top of that.
I need a better cooling unit for my PlayStation. It sounds like a jet taking off. I swear it does.
Does it have, has it been cleaned out? You've blown it out?
I ain't never even touched the thing since I got it. So I
It's
need
probably got a lot of crap in
to-
there.
Oh, no, I'm gonna clean it here soon because I swear you can get an airstrip and it probably sounds like that.
You have to wear ear protection.
I have headphones on whenever I turn it on. My friends, I'll be playing a game and they can hear it. And I'll be sitting back here on my PlayStation, it's like right there. And they'll say, "Hey Corey, PlayStation sounds like a jet taking off." I say, "Yeah, I know, I got planes going by right now." Sounds like it does, anyways.
Electrolysis is used to produce sodium metal and chlorine gas. All you have to do is split sodium chloride. So we would reduce sodium and oxidize chlorine. This is the Hall method for producing molten aluminum. All you need is you need to get the aluminum oxide, which is the bauxite ore, molten. And that takes a lot of energy to heat it up and melt it. So Hall and later Herold decided that if you add some of this sodium aluminum fluoride in there, it'll reduce the melting point.
How does that?
It's that's a good question.
Because it's just adding more, you think it make it increase it.
Yeah, I mean, according to our studies of colligative properties, but it does. It reduces the melting point, and cryolite. It's called cryolite, and that reduces the amount of energy required to run the process. And you reduce the aluminum ions into molten aluminum, tap it at the bottom. And it's so cheap now that we can wrap our food with it. You can electroplate your silverware. Right? Just be sure and run the electricity voltage through your force the electrons into your spoons or your flatware, and you can replate them. Here we're producing chlorine gas and sodium metal through this device. So you get your chlorine gas here. Then you take the sodium off and do something with it. Chlorine gas, a lot of that goes to, well, it goes to several places. One place it can go is to produce bleach. You can take this and make sodium hydroxide out of it, like the base, and then you can bubble this back through it and then make sodium hypochlorite, bleach. That's it. We're done.